Hello everyone, I am Masood Ibn Abdul Wahid. In this video, we are going to discuss about the solutions of some Anna University question paper problems. And the topic for today's class will be Kirchoff's laws. He stated two laws, Kirchoff's current law, Kirchoff's voltage law. Kirchoff's current law states that the algebraic sum of current meeting at a point is 0, whereas Kirchoff's voltage law states that in a closed loop, the algebraic sum of potential rise and potential drop will be equal to 0. So now we are going to discuss about the close relation between the three similar network solution methods. So we are going to see the comparison between similarities and differences between the Kirchoff's laws, mesh analysis and nodal analysis. So let us take this as a sample circuit and we will discuss the steps involved in solution of this network through this three methods. Let us take the solution of this network using Kirchoff's law. So the network is this one. Assume that the question asked us current through the resistance R3. So for that we have to assume some node namings. So we have assumed, and after that we will be assuming the branch currents by applying KCL, and we will be writing the loop directions, and according to the loop directions and the assumed current direction we will be writing the voltage equation, and we will have two equations for the given network and we will solve those two equations to get the required values. So if you solve the same network using mesh analysis, so the slight difference what we will be doing is, so this is the same network and we will be naming the nodes available in the network and we will be assuming the loop currents. These are the two loop currents we are going to assume. After this, the solution is same. So we will be writing the mesh directions, and according to the mesh direction and the mesh currents, we will be writing the voltage equations. And in this given network, we will have two voltage equations we will get, and we will solve those two equations to get the required value. And the same network, if we solve in nodal analysis method, what is the difference is, we will assume the node namings, and after that we will be assuming the branch currents using KCL, and those branch currents what assumed will be written in terms of an equation by considering one node at a time, and those current equations for each node will be written in terms of node voltages. That equation will be solved to get the required values. So these are the three network solution methods. The difference between the three discussed methods is, so if you use Kirchoff's law to solve a network or to find a parameter in a network, you need more number of equations. If you use mesh analysis, the number of equations required to find a parameter in the given network will be less when compared to Kirchoff's laws. If you use nodal analysis method to solve the same given network, the number of equations required to find the parameter will be less than that what number of equations required in Kirchoff's law and also mesh analysis. So in terms of equations, nodal analysis will reach out the solution quickly. So here we are going to discuss the logic which we are going to use here. Maybe you are well aware of that, but at another time we will discuss and go into the problem solution. So if we want to write a voltage equation, so definitely we will be having voltage rise and voltage drops. Where a voltage rises and where a voltage drops, we should know this. Okay. In terms of resistors, we will discuss the voltage rise and drop. So if the loop direction says that something like AB, across the A and B point there is a resistance with R1, and if we have assumed a current in the same direction of the loop direction, we can assume it to be a voltage drop. If the two directions are equal, it is assumed to be voltage drop. So we will start the voltage equation with a minus. Okay, so voltage drop, and it is starting with the minus, and according to Ohm's law, V is equal to I into R. So where the I in this case is I1 and the resistance R in this case is R1. So you have to multiply these two, minus I1 R1. In the opposite way, if the loop direction is A to B, and if the assumed current direction is from B to A, so in this case the two directions are opposite. So here we will logically meant it to be a voltage rise. So if it is a voltage rise, we will start it with a positive sign plus amount of the voltage is V is equal to I into R. So it is I1 multiply R1. So these are the two logical ways where we can meant the voltage to be a rise or drop. And we will go into the battery case, voltage rise and drop in batteries. So if we have a battery in this way, if we assume a current in this way, so according to the assumed direction, the current is going from negative to positive internally. So we are going to logically meant it to be a potential rise. What is the value of voltage? That is the battery voltage, whatever given. So if it is given with V1, so the potential rise will be for an amount of V1 volts. And in the opposite way, if the battery is assumed in this way and if the current is opposite. So in this, according to this assumed direction, the current is flowing from positive to negative polarity of the battery internally. It is meant to be potential drop. What is the amount of potential dropping? It is the battery potential given here it to be V1. So minus V1. We will go into the solution of a network. So there we will have even still better understanding about these 4 steps. So the given question is find V0 in the given circuit. And the circuit given to you is this one. So which is having 4 loops and the V0 is located across 1.5 ohm. The output voltage V0 will be equal to voltage across the 1.5 ohm resistor. According to Ohm's law, we know that V is equal to I multiply R. So the required voltage V0 is equal to I through the 1.5 ohm resistor multiply 1.5. So we need to find I. For that, let us use KCL and KVL. So to find the current, let us assume some node namings in the given circuit. As we are using Kirchoff's laws, we are going to use KCL to assume the current directions and we are going to use KVL for writing the voltage equation. So as you can see in the circuit, there is a current source and this 3 amps current is entering into the node A and we will assume a current I is leaving from the node A through this branch. And if this is 3 and this is I, the current through this branch will be 3 minus I, which is across the 3 ohm resistor. And this 3 minus I will be the incoming current for the node B through this branch. And there is one more 2 amps incoming current is there through this branch. And the current through this branch will be the addition of this 2, which is 5 minus I. And this 5 minus I is entering into the node C through this way. And already a 1 amps current is entering to the node C in this way. And the current in this branch will be equal to the addition of this 2, which is 6 minus I. And there are 2 incoming currents into the node D, which is 6 minus I in this branch. And already a current is coming in this way, which is I. So this 2 currents will be added and it will leave this node D in this branch. And if you add 6 minus I plus I, the remaining current will be 6 amps. So the 6 amps will come up to this point and after this point the current 1 amps will be returned to this current source and the remaining 5 amps will leave in this way. And the 5 amps will come up to this point and after this point the current 2 amps will return to this current source and the remaining 3 amps will current to this current source. So whenever you assume the current direction in a given circuit, see that your assumptions is logically correct. Even it is an assumption, the currents which is leaving the source should return into the source with the same value. In your assumption, if the current leaving from the battery is different from that what it is returning to the same battery, then there is some problem, some mistake you did in the assumptions. So you have to correct that by correctly assuming. In our assumption, in our case, the currents leaving from the respective source are returning with the same values. We are in need of finding the I. We will write the voltage equation of this loop A, B, C, D, A. Let us assume that the loop direction is A, B, C, D, A. So we are going to write the voltage equation of this loop A, B, C, D, A with the help of Kirchoff's voltage law. So branch by branch we will write the voltage terms with the discussion that whether it is a potential rise or drop. So let us take the first two nodes, which is A, B. So between A and B, if you see, we have a resistor of 3 ohm and the current through that resistor is 3 minus I. So the traveling direction is AB. The current direction is also from A to B. So both are same. So it is a potential drop. So we will start with a minus with a value of IR. I is 3 minus I. The resistance value is 3. And now we will move from B to C. So between B to C, there is a resistance of 2 ohms with a current of 5 minus I. According to the assumed current direction, the loop direction and also the current direction is same. So again it is a voltage drop. So we will start with the minus of that current value 5 minus I multiply with the resistance value 2. Now we are moving further from C to D. So it gives you, between C and D, there is a resistance of 1 ohm and the current through that resistance is 6 minus I. So we are having both the directions to be same. So it is a voltage drop. So now our loop direction is D to A, but the current direction what we assumed is A to D. Both are opposite. So it is a potential rise. So start with the plus with the voltage value of I multiply R. The current is assumed to be I and the resistance is given to be 1.5. There is no batteries in the given loop, so the summation of all these will be 0. By simplifying the written equation, we will end up with this equation from which you can group all the I terms together and the constant terms together, which will result in this equation, and move the constant term to the other side, which makes minus 25 to be plus 25. The current I can be written as I is equal to 25 divided by 7.5, which can be calculated as 3.33 amps. So the current what we assumed I, it is found to be 3.33 amps. So this current you can substitute in the required place to find V0. So V0 is equal to 3.33 multiply 1.5, which will give you the required output voltage. V0 is equal to 4.995, approximately 5 volt. We're going to simulate the same network what we have just solved and correlate the answers with the simulation result. For reducing the duration of the video, I have already drawn the circuit in the Proteus software. So those who are watching the video first time, so please go back to my previous videos and know how to use the Proteus for drawing a diagram step by step in my previous videos. So for the others, so just I will let you know how to pick the current source, because this is a new element which we have in this problem. So as usual, go to the pick devices and type current source. So for the current, need not type the word current fully. So just type C and source. So as you start typing current source, you will end up with this. So now after taking the current source, you can draw the circuit as given to you. And now I am going to run the simulation for cross-checking the answer. I am running the simulation. And you can see the ammeter which is placed along this loop, for which we assume the current value to be I. It is measured to be 3.33 amps. So the current what we have calculated is also I is equal to 3.33. What we have calculated is correct according to the simulation. And the voltage across this 1.5 ohm resistor, which is termed to be V0, output voltage V0, it is also measured to be 5 volt, which is again we have calculated to be the same. With this, what the manual calculation we did is aligning with the results what we are obtaining in simulation. In today's video, we have learnt about the similarities and difference between the three network solution methods, namely Kirchoff's laws, mesh analysis and nodal analysis. and we took one problem from the Anna University question paper and we have solved it. We have tested the answers with the Proteus simulation results. So thanks for watching. So let me sign off with a closing note that in the next video we are going to take one more problem which is again from Anna University question paper. Thank you.